Why is basic chemistry so difficult? No, really, why is basic chemistry so difficult? I mean, in schools we often learn about, obvious rules governing chemical reactions, electronegativity, oxidation states, so on and so forth, but why do they actually happen? Why do molecules bond? Why are we even doing chemistry in the first place? Why? Well, those are the questions I'll be answering today. Not giving you a list of things to memorize to do chemistry, only answering why. Why we do chemistry in the first place. And so I suppose there will be no better place to start than with the simplest thing, the atom. You see, the way the atom works is we have positively charged protons, neutral neutrons and negative electrons. In the center, the nucleus, we have the positive protons and neutral neutrons, and because of that, the center is positive. That's why when we have electrons just floating around, chilling in the void, these negative electrons will naturally get attracted to the positive nucleus and cloud around it, forming an electron cloud around the nucleus. And okay, so far it already has been a fair bit of information, but all you need to remember is that in the middle of the atom we have something like a positive side of a magnet, and around it we have a cloud of the electron, which is like the negative side of the magnet. And both of them just come together to form an atom. But why do they form an atom? Things in our universe want to lose energy. This may seem a bit counterintuitive at first, but once you get used to the fact, you begin to see it everywhere. The reason why things move, the reason why things change, the reason why things happen is because everything wants to have as little energy as possible. So when an object has a lot of energy, it tries to convert that energy in any way possible to lose it. For example, right here, this object has a lot of potential energy. Because it's really high up, you see. That's because of gravity. Now, I am actively holding it in place, because if I were to let go, it will just fall. What's basically happening there is that the second I let the object go, it's converting all this potential gravitational energy into kinetic energy by falling. And then it ends up on the ground with low potential energy, so low height, and low kinetic energy, so no movement. The same thing happens for our electrons. You see, when they are close to the positively charged nucleus, they have less energy. And now to that you may say, electron wants to get rid of its potential energy and so is getting as close to the nucleus as possible. Shocker. But there is more to it, and whilst your comment was incredibly intelligent and insightful, which honestly isn't all that surprising from someone this smart and good looking, the detail here is the fact that in order to get lower energy, you sometimes need to do different things. And that's where we get shells, subshells, orbitals and so on. Here's how it works. We have the electron cloud, which is divided into shells, which are then divided into subshells, which are then divided into orbitals, which are then divided by spin. Now we can think of all of them like this. Electron cloud is all of the electrons in the cloud. When it comes to shells, you can think of them as the distance from the nucleus. When it comes to subshells, you can think of them as the shapes of these electrons. When it comes to orbitals, you can think of them as the direction or orientations in which it's shaped. And when it comes to spin, well, spin is just a thing that electrons have. There's nothing in classical mechanics that works like electron spin, but just a property of electrons which can be described using angular momentum, or rather like angular momentum. Just take an electron, give it direction which it's spinning, and even though it's not spinning, the equations for spin still predicted everything nicely. So scientists were like, close enough, should be fine. This is where we get our quantum numbers from. The principal quantum number telling you on which shell the electron is, so basically how far an electron is from the nucleus. The azimuthal quantum number telling you on which subshell it is, so how complex the subshell is. The magnetic quantum number telling you the orientation of the orbital, and the spin quantum number, which is just spin. Now that is a lot of information, so let's go over this once again. Each electron has 4 values to describe it. First, principal quantum number, so basically how far it is from the nucleus. Then azimuthal quantum number, so how complex it is. Then magnetic, so like the orientation, and then spin. And right here you can see how we can specify each and every electron using only these numbers. Now there are two more wrinkles to this. You see, first of all, chemists wage a secret war against math, and because of that they actually replace the characters for subshells with SPD and then F and so on. It doesn't actually change the meaning, these are still numbers, it's just that chemists thought that would be too simple to use numbers to represent numbers. And then another thing, whilst we can tell on which shell and subshell an electron is, we can't really do the same in the same way for the orbitals. And that's why when we denote the orbital configuration, we note down the shell, the subshell, and then just how many electrons there are. Like this. That's because, due to quantum mechanics, asking something like on which orbital is the electron kind of loses its meaning, sort of, so yeah. Anyhow, these are all the possible ways electrons can be arranged, but which ones will they actually pick? Well, just like if you have a ball, you need more energy to move it further away from the massive gravitational planet, and if you have an electron, you need more energy to pull it further away from the nucleus. That's why electrons will first start with the lowest shells, it's because they need less energy to occupy them. Next we have subshells. Now each shell has its shell number of subshells, which she sells seashells on a seashore, but what are these subshells? Well, I always like to think of them as shapes, so 0th subshell is just a sphere, subshell 1 is a bit more complex, subshell 2 even more complex, and so on and so forth. Energy-wise, the basic idea is obvious. The more complex the shape, the more energy it requires. Kind of intuitive. But there is a wrinkle. Because what would require more energy? A simple but large subshell, or a smaller but more complex subshell? Well, the answer is... it depends. Fortunately, there's a pretty simple way to visualize how energies go, because they go like this. So add together the shell number to the subshell number, and you want to start the smallest one. It works much better with the arrows. And there, this orders the energies. Which may not be exactly clear right now, but don't worry, I will come back to it soon. So that will be that, energy-wise, because next we have orbitals, which are like orientations of the subshells. In this case, energy doesn't really matter. What does matter is the fact that on each orbital you can have 2 electrons, both with different spin. Now with all of this knowledge combined, we could actually just take all the shells, divide them into subshells, divide them into orbitals, order them in a way where the higher the orbital, the more energy it needs, and there, a graphic representing exactly how much each electron needs depending on its shell, subshell and orbital. And yeah, I didn't make that graphic, it's from ptable.com, which is an absolutely amazing website, and right there you can actually click on different elements, see the orientation, but all that in mind, I hope you understand now how energies of electrons in a single atom work and what all of these squares mean. Right here you can see all of the respective orbitals. Now in relation to these 4 things, you can describe the, in quotes, position of an electron, and based on that position we can get how much energy our electron needs to be there. And so just like with all the things in our universe, electrons want to have as little of energy as possible, so they will naturally try to fall as low as possible in a single atom. But what happens when we introduce another one to the mix? Okay, for the sake of simplicity, let's start with 2 hydrogen atoms. They both have an electron and it's about as simple as you can get for non-ions. The 2 simplest atoms possible. What happens when we bring them close together? Well, we have our s orbital, and so we bring our 2 s orbitals together, both of them with a single electron, and they merge and combine into a bonding sigma orbital and anti-bonding sigma orbital. Alright, so I suppose an explanation is in order, and a fair warning, this will be the most difficult segment of the video. So if you struggle with the understanding what I'm about to tell you, feel free to rewatch it a couple of times and don't feel bad, because this is literal quantum mechanics. So, basic idea looks like this. In quantum mechanics, for each particle, we don't know its exact position. We only have a function describing the probabilities of them being in any spot. It's called a wave function, represented with a character psi, and basically tells us the information about the particle. So between these 2 points, high probability. Between these 2 points, low probability. Right here a bit bigger, and so on. Now this function can go up into positives and down to negatives. It's a long story, okay? I will probably make another video on quantum mechanics soon to clear it up, but just bear with me here. And so that's why we always square this function in the end, so that if it happens to be a negative number, it just gets squared into a positive one. And voila! We get a function describing the probability. Cool, now what happens if we add another particle to the mix? If we have 2 particles, then there are 3 possibilities for how they could interact. They can be in phase, in the positive, out of phase, or in phase, in the negative. Now let's consider what happens when they come together. First we need to bring these 2 functions close. Now we need to add them. Now we need to square them to remove the negative probability.
Right here you can see that actually it doesn't matter if they are in phase in the negative or in phase in the positive. When we square them, they just end up as the same function, they are equal. Which means that with two electrons there are actually two possibilities on how they could bond. They could either bond in phase, which glues them together and requires less energy, or they could be out of phase, which pushes them apart and requires more energy. So, which one will our electrons choose? The easy one, of course, the one that requires less energy, the bottom one. And that's why two hydrogen atoms bond into a hydrogen gas molecule. It's because when bonded, this is the wave function of the electrons, and this wave function requires less energy, and so our hydrogen gas molecule has less energy than the atoms apart. And that is the quantum mechanical explanation for why molecules are more stable than atoms. If you understood this, then congrats! If you haven't, once again, don't feel bad, rewind the segment. This is the most difficult concept of the video, and it's something that would normally get taught way later on than at the beginning of a YouTube video about chemistry, but yeah, this is an honest and true quantum mechanical reason hydrogen gas requires less energy than two hydrogens. But what if we add more electrons to the mix? What if our hydrogens have two electrons each, not one? Well, then these electrons would go onto the anti-bonding orbital, and nothing will happen. The anti-bonding orbital requires more energy, so we gain 2 electrons worth of energy, and we lose 2 electrons worth of energy, which is equals to 0. I mean, why would they go to trouble of bonding if they won't lose any energy out of it? That's why even though hydrogen gas exists, for helium gas it's just helium. None of them are bonded because their orbitals are full. And so this is actually quite curious. That's because from here we can see that if both orbitals, which are bonding together, are full, then we won't end up with a bond at all. That's because we'll have 2 electrons which give us energy and 2 that take it away, so these don't actually do anything when it comes to bonding. Now, since full orbitals don't do anything when it comes to bonding, and we fill electrons from the bottom up energy-wise, it means that we don't actually care about all of these electrons right here. They'll just cancel each other out anyway, and we only care about the topmost shell, the valence shell. That's what chemists call the outermost shell. Valence stems from exactly that. It's just that chemists think that they sound really clever when they say stuff like, "No, it's a valence shell." Just say outermost like a normal person, you atom bonding, ion charging, vial taking, carbon base oxidized. I digress. And so that's why we only care about the valence shell, and also why there are certain atoms out there which are significantly difficult to bond. For example, helium. Since its valence shell is full, there aren't any electrons that are up for grabs. Another example would be neon, or argon, or krypton, and so on. Now, since they are so difficult to bond, they won't actually reform any of the more complex structures, more of that later, and just chill as a gas. So we can just call them noble gases. And so that's the in-depth explanation of why atoms bond. Except there's a bit of a problem. According to what I've said so far, hydrogens can bond into a molecule. Helium can't. But what about the hydrogen and helium? Well, technically we're still gaining more energy than we're losing, but why don't we ever see anything bonded to helium?
And I do really want you to appreciate that fact. Given what I've told you so far, it really seems like helium hydride, neutral helium hydride, should exist. Yeah. Really, there's no contradiction. This is not a trick, really. Based on what I've told you so far, it should exist. However, if you ever try to go and look for a neutral molecule of helium hydride, you will find that it's pretty annoying and it's pretty difficult to find any. The best source, seriously, best source I have found for the existence of a neutral molecule of helium hydride is this paper from 1985, if I do remember correctly, and this sentence, where they specifically differentiate between helium hydride ion and helium hydride, which means that at least hypothetically it should exist. That's the best source I've got. So why is that? Why is that in theory this molecule should be completely fine, but in reality there's almost no sources actually confirming its existence?
Well, imagine hydrogen and oxygen gas. These molecules have a lot of energy in them. Then on the other side we'll have water. Water has less energy. Right here, I'm taking their complex bonding structures and just simplifying them into a single number. So hydrogen has unstable bonds, and so a lot of energy to be gained. Water has more stable bonds, so it's difficult to extract energy out of it. This is the exact same energy as from the bonding orbitals in the previous chapter. Now, the way reactions are often introduced is simple. You have the reactants and the product, and in between them, the arrow. But this arrow is hiding something really important. That's because even though most people have seen these sort of reactions, most non-chemists don't actually know what this arrow represents. That is, the transition state. You see, whenever I animate a simple reaction like this, I like to simplify it like so. Break down the atoms and have them reform into a product molecule. That's why if we graph the energy of this reaction, you can see that we start with the initial energy, then we need to give it some energy to start the reaction. After that, our reaction starts and we get the energy back plus some extra. That's the gas, that's the spark, that's the fire, heat and explosion, that's the water. There is one problem with that, however. Separate atoms are insanely high in energy, so if in our reaction they really broke down into individual atoms, it wouldn't look like this, only like this. So the question remains, what happens on this peak? Well, it's the transition state. You can think of it as a highly unstable molecule that forms from these atoms. It requires much more energy than either the reactant or the product, but serves as an in-between mid-reaction. Now, why would that be important? Well, it's because this transition state is kind of blind to the reaction itself, which means that once our hydrogen and oxygen gets to transition state, it could actually go either way. It could turn into water, or it could go back into a gas. So what does that mean? Well, think of it this way. We start with hydrogen and oxygen and we ignite it with a spark. Now from there we have two possibilities. It either turns into water or it turns into hydrogen and oxygen. Now if it turns into water, end of story. You can't burn water. But if it turns into hydrogen and oxygen gas, it still can explode. So if it gets that energy again, it once again has the choice to either go back to being a gas or turn to water. Now the point here is that the single molecule can actually go from being a gas back to being a gas, but that's for a single molecule. For a group of molecules, this process will repeat over and over again until we end up with only water. That's the statistical aspect of chemistry. Now why is that important? Why should we care about this distinction between burning it one way and burning it with probability? Well, besides the obvious point of it's important to know what the reactions are instead of what we would like them to be, there is another practical reason. Consider electrolysis. When you're electrolyzing water, you go back, you turn it back into the transition state, and this time you end up with some hydrogen and some oxygen. So why doesn't the hydrogen burn? Well, it's because it just floats away. Okay, the reality is a bit more complex, but it's irrelevant for now. So this time, our scenario reverses. We're electrolyzing water and it either turns back into water to get electrolyzed again, or it just turns into hydrogen and oxygen gas, which floats away. And that's why you can produce hydrogen and oxygen with electrolysis. And actually, on a side note, that's why electrolysis results in so many fun chemicals, like acids or flammables and so on and so forth. It's because it can actually create higher energy molecules by kind of forcing them into this higher energy state. And what a coincidence, on Harry's channel, Scrap Science, there is a brand new fresh video specifically about electrolysis, for which I've made some admittedly tiny animations. So hey, go check it out. And I know it's been a lot, and just crazy amount of information that you dump on you, but let's just take a second to appreciate how far we've come. Starting with the basic elementary properties of the electrons, and from there, step by step, we've created an exact description of why and how you can turn water into oxygen and hydrogen and vice versa. And oh my goodness, isn't this refreshing? Instead of valence shells and pi bonding and all the stuff you need to memorize, you have basic rules, the way they interact with each other and their consequences, up to the point where things are actually kind of obvious. For example, molecular scales are actually large enough so that we can apply more classical mechanics to them. So when it comes to two molecules, you can think of them as actual physical balls, really smashing together. In order for a reaction to occur, you need to smash them together strong enough, obviously, but also things like the rotation of the molecule matter, things like vibration of the molecule matter, things like molecules around it matter, and so on and so forth, and that's what's so lovely about theoretical chemistry. What you have to remember is that these molecules are in the same universe as us, same physics, same laws, and so on these scales, they actually behave in a pretty much same way. Just like if you have some stacked cubes, you want to topple them, not only the energy of the projectile matters, but also the orientation from which it's coming, and how it hits it. And we can consider this to be a high energy state, this to be a low energy state. This is just like chemistry, not only in the sense that it's an analogy, but also in the sense that the physics is the same. The only difference is that right here we're dealing with gravity, right here with electromagnetism. But that's kind of the only difference. And so at the end of this chapter, the question remains, if it is really this obvious, if it really is this intuitive, why isn't chemistry taught this way in schools?
So then the obvious question arises, why isn't chemistry taught this way in schools? My theory to why this kind of chemistry isn't really being taught in schools is that it involves a lot of quantum things, which is a big problem because quantum mechanics by itself isn't a difficult field. Yeah, it may be complicated, may have a lot of fancy words, but by itself, quantum mechanics is really simple. In reality, in depth, they are all pretty intuitive. I suppose that would be the point of the video. For most fields of science, they aren't as difficult or complex as people make them out to be. And most of the time, the actual difficulty and complexity comes from the explanations rather than the underlying topics. Okay, but then, why is that the explanation? Why is chemistry explained this way? Why are we asked to memorize all of these different things? And what actually are those things? Like, for example, why do we have to memorize all of this information about states of matter?
Okay, so let's start with something simple, like the 3 states of matter: solid, liquid, and gas. What are those states? Well, first we have solids, rigid, lowest in energy, and with an unchanging shape. Solids exist at low temperatures and high pressures, with one example being ice. Next we have liquids, fluid, high in energy, with a shape that can change but cannot be compressed. Its volume is constant. They exist in the in-between zone of temperature and pressure, an example being water. Then there is gas. Highest in energy, not only can it change its shape to fill a container, but it's also compressible. It exists in the highest temperatures and pressures, like steam. It's actually pretty obvious why they occupy the spectrum in this way. If you consider that solid basically means a bunch of particles as tight packed as possible, liquid is similar except the particles have much more energy so they move a lot more, and then there is gas, where they also move but it's not dense enough to slow them down in a significant way, so they just keep on bouncing. Now these are 3 different states of matter, but some of you out there might be right now screaming at your monitor screen, make it! There is one more state of matter you haven't mentioned yet, and you would be wrong. Yeah, there isn't one more state of matter I forgot to mention. There are many states of matter I forgot to mention. Okay, so everybody knows about plasma. That's the state of matter which is basically like gas except more, even higher temperature, even more aggressive molecules, and some other shenanigans. But that's about it when it comes to what you would normally learn in school. The next couple of chapters would be probably about how different molecular structures affect the boiling point, why water is so bizarre and acts in a different way, and then different rules governing these states. But I'm not here to teach you chemistry like it's taught in school. And that's why now it's time to talk about crystals. Now you might be wondering, what do crystals have to do with states of matter? Aren't crystals just solids? And yeah, some of them are. But what about liquid crystals, like in LCDs, so liquid crystal displays? Are they a solid or a liquid? Or what about superfluids? Should we group them into the same category as something like water? Or what about quark matter, degenerate matter, string net liquid, or even photonic matter, which is just as nonsensical as it sounds? What about all of these? Well, should we group them into these 4 categories? No, we shouldn't. That's because that's not why states of matter exist. The reason why states of matter exist, the reason why things like covalent or ionic or metallic bonding exist, isn't for us to group everything into these neat categories because everything has to fit. The true reason is because it's convenient. We say that something is liquid simply because it's easier than listing all of the properties of a substance, and that's actually what's so bizarre in my opinion when it comes to chemistry.
The problem is that in schools, you're just being taught all the rules without the underlying explanation. And that would be the thing to remember. Every single rule in chemistry, and all the fields of science too, always will have an underlying explanation. That's because people aren't robots, and even the scientists that came up with all of this weren't robots either. They also needed some sort of way to understand the topic, some sort of way to grasp it in human terms. However, those rules are still important. It's because they just make our lives easier. I mean, you could do the same thing in physics if you wanted to. Instead of using all of these equations, different from astrophysics to classical mechanics to relativity, you could just use the Schrodinger's equation for everything. It would be painful, you probably wouldn't be able to do it, but you technically could. The same applies to chemistry. You could just use, actually, the Schrödinger's equation to describe all of chemistry. But that's tedious, that's difficult, that's basically impossible for us currently. And so that's why we have all of these rules. But these rules aren't a must. There is an underlying truth, something that you can understand, something that you can grasp. And so with this video, I really hope I've given you a different perspective at chemistry. Not the one with all the rules and the memorization, only a more intuitive one. Something with the basic concepts from the ground up. Something that's actually pretty simple and hopefully obvious. And I really hope that you've learned something. I really hope that my explanation was good enough. And I really hope that you finally realize that chemistry isn't what you think it is. And my glasses are broken. They're missing the thing. I really will have to buy a new pair. This is ridiculous. Hi, it's me, MAKiTs, the guy who just made the video you've been watching right now. I hope you appreciate me almost setting my entire office on fire for a chemistry video. That was fun. If you'd like to see all the behind the scenes of me doing a big fire and spilling a lot of flammable liquid everywhere. Cheers! Oh, I love my job. Then I would recommend my Patreon, where that is available right now, and also was available before this video was even finished. Oh, isn't that a steal of a deal? Over there you can also chat with me if you want on Discord. I have a Discord server, in case you'd like to join. I stream literally every single day on my YouTube channel called Charity Checkups. We're streaming for charity. Right now we're collecting money for Prevent Cancer Foundation, a fundraiser called Cancer Bad. Thank you so much, Atomic, for the name. Anyway, I'm gonna go. I have more videos to work on. And I suppose for now, that'll be it. Thank you everyone so much for watching, and have a great day. Bye.